I'm now going to share more worked examples of problems that are exactly like problems you'll encounter on your next exam. The worked examples I'm going to share in this video pertain to problem set number 6. And so to start, we're going to do problem number 4 from problem set number 6. In this problem, we are told that we have a runaway grocery cart. I'm representing that grocery cart as a single point mass, as you see as this blue dot. We're told that it's a runaway grocery cart, which means it has some velocity. And let's go ahead and have our positive x be to the right, positive y be up. In this problem, we're only dealing in the horizontal direction. Our spring is oriented completely horizontally. The spring is represented in gray. What's happening here is at first the spring is at some equilibrium length. I'll draw like a dotted line here to help you better visualize the equilibrium length. So what's happening is at first you have the cart moving to the right. The spring is just sitting there at its equilibrium length. Then at some time later, you're going to have the cart just touch the spring. It's still at its equilibrium length. But what's going to happen next is as the cart is moving to the right, the spring is actually going to be doing work in the opposite direction of the motion, which is to say, you can imagine that there's some Hooke's law equal to the spring constant K times delta X, where delta X is how much the spring has compressed from its equilibrium length. So if you can imagine you have the cart moving to the right, it hits the spring, it keeps moving to the right, but now it has this Hooke's law K delta X force going to the left. So if the motion is to the right and the force is to the left, what's happening is the spring is doing negative work on the grocery cart. Now, spring forces, like gravitational forces, are conservative forces, which is to say that if they do negative work, that negative work can be reclaimed later on in the form of positive work that can increase the kinetic energy of a mass. So what's happening in this problem is that originally we just have kinetic energy in the grocery cart. This grocery cart right here, we are told that it has a mass equal to 12 kilograms. And so the kinetic energy of this grocery cart is just 1/2 times its mass times its velocity squared. So originally we can think of there being kinetic energy in the cart, and because the spring is not being compressed or stretched, there's no potential energy in the spring. Then they collide, and then after collision, you see the spring start to collapse. And when it does so, it is exerting a force opposite the direction of the motion of the cart. So you can imagine the cart, because it's going to the right, and there's this force from the spring on the cart that's going to the left, this is a deceleration. The acceleration is opposite the direction of the motion, which is to say that eventually the deceleration is going to take all of the kinetic energy away from the cart. And so there's going to be a moment when the cart comes to a stop. And at that moment, how much the spring got squished, this delta X term, stored in the spring is an elastic potential energy that is equal to 1/2 K delta X squared. Okay, so this is the example of the spring was doing negative work, and as it was doing more and more negative work, it was storing up elastic potential energy, such that if we continue, then the spring is going to start accelerating the object back to the left. That means that the potential energy is now being converted back into kinetic energy, but now the cart will be going to the left. So the key here is that we start with energy purely in its kinetic form, and at the moment the cart comes to a rest and the spring is squished by an amount delta x from its equilibrium position, we can say that what was originally kinetic energy, that's this right here, has now been converted to elastic potential energy. That's this right here. And this is the key to solving the problem. I want to review one more time. Potential energy is when the spring does negative work. So right when the cart touches the spring to when the cart comes to a rest, all of the points in between, the spring is exerting a Hooke's law force opposite the direction of the motion, because the cart is going to the right and it eventually is slowing down to the right, comes to a momentary stop, and then it's going to go back to the left. When it starts going back to the left, what's happening is that potential energy that's stored in the spring is now doing positive work, because now when the spring is pushing to the left and the cart starts moving back towards the left, the force is in the same direction as displacement, which means it's positive work. But when it was doing negative work, that is when it was slowing the cart down, when the force was opposite the direction of motion, potential energy was storing up. And for a spring, we call it elastic potential energy. And so we, by energy conservation, if there was no other net forces acting in this problem, we can say that the original kinetic energy, 1/2 mv squared of the cart, is going to be equal to the elastic potential energy stored in the spring at the moment that the cart comes to a stop after it's squished the spring by a displacement delta x. And so at this point, we can just do algebra. We see that there's a 1/2 in each side of that equation. And what I can do is I can divide both sides by m such that I can have a v squared equal to k, which is the spring constant, divided by m delta x squared. And of course, I can take the square root of both sides such that v is equal to the square root of k over m delta x squared. To simplify, this is the same thing as k over m delta x squared. And since I have a delta x squared as a discriminant in a square root, the square root of delta x squared is just x squared. And so this is just equal to the square root of k over m delta x. And we have everything we need to solve this problem, because we were told the mass, and that of course is this term right here. And then we want to know what this k term is right here. Well, k was given to us as well. K in this problem is equal to 270 newtons per meter. So finally, we need to know, and just to be thorough, I'm going to write the mass down here as well. We also need to know what our displacement delta x was. Remember, that's how much the spring squished up from when the runaway grocery cart just touches it to when it momentarily comes to a stop. That's when the spring is going to be squished up the most. At any points after that, the spring is now going to start to expand again, and it's going to start to push the cart back to the left. So we are told that it's 63 centimeters. So delta x equals 63 centimeters. And we can convert that more specifically. 1 meter equals 100 centimeters. Centimeters cancel. I'm now in units of meters. And when I'm dividing 63 by 100, I have to take the decimal point 2 places to the left. So that's equal to 0.63 meters. And this delta x that I'm circling in blue, that goes right there. So you see, you have everything you need to solve for what the original velocity of the cart was. It's the square root of k over m. K is the spring constant, which you're given. It's this 270 newtons per meter. You're given the mass of the cart. That goes in for m. You take the square root of the ratio of k over m, and then finally you multiply by the amount in which the spring was squished from its equilibrium length to its maximum squishing length, if you will. That is the point when the mass comes to a rest. And when that mass comes to a rest, it means that the kinetic energy that was originally in the mass has now gone into the form of elastic potential energy stored in the spring, because the spring was doing negative work on the mass as the mass was moving to the right, and the spring force on the mass was acting to the left. When a conservative force like a spring does negative work, it means potential energy is being stored. So at the moment where the original kinetic energy is gone, if there were no other net forces acting on the system, we know that all that energy now must be in the form of elastic potential energy. And that's what allowed me to write this key equality right here. 1/2 mv squared, where m was the mass of the grocery cart and v was its initial velocity. That initial kinetic energy on the left can then be equated to the elastic potential energy on the right when the cart comes to momentary stop. K being the spring constant and delta x being the amount in which the spring compressed. So that is problem number 4 from problem set number 6. This is problem number 6 from problem set 6. In this problem, we're told that there's a 2.6 kilogram block, so that's why I write mass is equal to 2.6 kilograms. And it's attached to a horizontal rope. So I'm going to represent the block as this green block you see here. And it's going to be on some surface where we're going to have to take into account friction. This is not a frictionless surface. We have to take into account friction. And so I'm going to represent a dot as the center of mass of that object. And I'm going to draw a free body diagram. I'm going to use the conventional to the right horizontal is positive x and upward vertical is positive y. And so if we have a rope attached, that means that there is some force due to the tension of the rope that is attached to the block. If the block is being accelerated to the right by the tension in the rope that's attached to it, that means that there must be some force from the kinetic friction. And then we also have to take into account vertical forces. Because this block has some mass, that means it has some gravitational force, mg, pointing down. And because the surface has an action-reaction pair with the block being pushed against it by gravity and the surface pushing back on the block, we're going to say that there's a normal force on the block upward. We've got our free body diagram now, and so that allows us to write two equations. It allows us to write an equation for the horizontal direction and an equation for the vertical direction. Let's go ahead and do the vertical direction first. Some of our forces in y are equal to the normal force, which is positive because I'm having positive y be upward, minus mg because mg is downward y, and I can say that that is equal to the mass times the acceleration in the y direction. If this is a problem where the motion is only happening horizontally, then there is no acceleration in the y direction, and so this is equal to 0. This allows us to say that the normal force is equal to mg. I just added mg to both sides. That's going to come in handy when we need to determine the frictional force, because the frictional force is the product of both the nature of the surface and also to what degree that surface is being pressed against another surface. The second equation I can write with my free body diagrams is the sum of my forces in x. And in this problem, it's going to be the force of tension. And again, that's the rope that is attached to the block and pulling on it horizontally. And since I have to the right being positive x, I'm going to have that have a positive value. And then I'm going to have a negative value for the coefficient of kinetic friction. This coefficient of kinetic friction can be expressed as the product, the force of kinetic friction can be expressed as the product of the coefficient of kinetic friction multiplied by the normal force. So I'm going to say that this is, again, the force of tension minus, and now what I'm doing is I'm rewriting this term right here. And so by rewriting this term, I have a coefficient of kinetic friction. That's this value that we've already been given, multiplied by the normal force. So this is the nature of the surface. You can imagine that sandpaper would have a higher coefficient of kinetic friction than ice. And this is the nature at which the surface of the block is pressing against the surface that has friction. You could have a really rough surface, but if it's barely grazing another surface, there's not as much friction as if they're really pressing a lot against each other. And so the more the normal force, the more the block is pressing up against the surface. I can further rewrite this because I have the normal force being equated to mg, and so this is equal to the force of tension minus the coefficient of kinetic friction times the mass of the block times g. Okay, this is going to be handy because now to solve this problem, I have to think about work. And work is going to be force acting over distance. And so in the vertical direction, the forces cancel, and so there's no work happening in the vertical direction. However, in the horizontal direction, the force of tension from the rope attached to the block is not precisely balanced by the kinetic friction. There's a net force going to the right because this block is being pulled to the right. So that means that there's work being done by the net force to the right. So we're going to have to take into account what is this net force. Before I go any further, I'm going to say that the net work being done on the block is going to be equal to the sum of conservative forces acting on the block plus non-conservative forces acting on the block. In this problem, gravity is a conservative force, which is to say that if gravity was doing negative work on this block, gravitational potential energy would be storing up, which is to say that eventually that gravitational potential energy can be translated back into kinetic energy of the block. We can get it back. That's what it means to be a conservative force. Springs are another example. If you squish a spring, when that spring squishes, there's elastic potential energy that's stored in that spring that we can get back by the spring starting to expand and pushing back, and therefore providing an acceleration and therefore increasing kinetic energy again. You can get it back. However, in this problem, the conservative force of gravity is acting in the vertical direction, but there's no work being done in the vertical direction because the pull of the block against the surface is equal and opposite the normal force pushing back. They're an action-reaction pair. And so in this problem, there's no work being done by conservative forces. This means that we are left with just the horizontal direction, and to determine the work that is done in the horizontal direction, we have to perform an integral where we integrate from the initial x position of the block to the final x position of the block. And then we have to integrate the net force in the x direction dx. In this problem, our free body diagram tells us that the net force is going to be equal to the force due to tension minus mu k mg. And then I have my dx term. Now, here's a key in the problem. We are told that the force that is acting on the block from this rope that's attached to it is not constant. It actually varies as a function of position. And more specifically, we are told that the force due to the tension is acting exclusively in the x direction, and it's equal to 20 minus 5x. That's in units of newtons. Do you see how at different locations, right? This is an x location, this is an x location, this is an x location. At different x locations, that force is going to have a different value. It's not a constant. So we need to integrate this, and we need to keep it in the integral. We can take constants outside of integrals, but we have variables here that are changing as a function of x, and so we have to keep that in the integral. So what I'm going to do now is I'm going to integrate from x initial to x final, and I'm going to substitute for this tension force 20 minus 5x. And then I have to subtract mu k mg, and all of that is multiplied by dx. We are also told that our x initial and our x final have a difference of 3.8 meters, because we're asked what's the block's speed when it's been pulled to x equals 3.8 meters. So we'll go ahead and let the initial x be 0, and we'll let x final equals 3.8. So this x initial is 0, and this x final is 3.8. So we need to compute this integral. To compute this integral, we are going to have a 20 dx term. And so 20 dx, when you integrate it, is just going to be equal to 20x. If you can imagine, if I took the derivative of that, if I took 20x dx, then x would go to 1 and just be 20. I then have a minus 5x dx. And so to integrate that, I'm going to have minus 5/2 x squared. You see, if I took the derivative of that, I'd have 2 times 5/2, which would be 5x. And then I also have a minus mu k mg dx, and so the integral of that is just minus mu k mg x. And I'm going to evaluate this from 3.8 equals x to 0. So you can imagine I would take 3.8 and put it in for each of those x terms, and then I would take that value and I would subtract when you put 0 in for all those x terms. And by the way, if you put 0 in for all those x terms, every single one of those terms is going to vanish. So really what you see here is just you have 3 terms. One involves an x, one involves an x squared, another involves an x. And each of those you put in 3.8, and that's the value you're going to be working with. In the interest of real estate here with my screen, I'm going to leave it in this form instead of plugging in the numbers. But again, I just want to say, when it comes to this term right here, you just take 3.8 and you put it in for x, so 20 times 3.8 minus 5 halves times 3.8 squared minus mu k mg times 3.8. And then that's all, because the other part, the 0 part, if you were then to subtract when you put zeros in, well, 20 times 0 is 0. 5 halves 0 squared is 0, and mu k mg 0 is 0. So you just plug in 3.8 for x. So that is going to be the net work that is done when you take into account the rope pulling to the right, but kinetic friction countering the motion to the left. That's the net work that's being done. So a key move now is recognizing that the net work done on the block is equal to the change in kinetic energy of the block. This is the work energy theorem. We know what the net work on the block is. That's this right here. The change in kinetic energy of the block is going to be Ke final minus Ke initial. That's equal to 1/2 mv final squared. That's the final velocity of the block after it's been pulled to x equals 3.8 meters minus 1/2 mv initial squared. That's the initial velocity of the block. And remember, the block was initially at rest. That's why we say v naught equals 0. And so that means this term vanishes. So now I can multiply by 2 and divide by m to isolate vf final squared, which is what I want to solve for. Again, we're asked, what is the block speed when it's been pulled 3.8 meters? So let me remind you that this is equal to the net work, and the net work we already computed. That's what I'm underlining in red. So now what I have is 1/2 mass of the block, whatever the final velocity is after it's been pulled 3.8 meters, v squared, is equal to 20x minus 5/2 x squared minus mu k mgx, and that's evaluated at x equals 3.8 and x equals 0. This is where I said you could multiply by 2 and divide by m. I can say vf squared is equal to 2 over m, and then I'm going to write this quantity again, 20x minus 5/2 x squared minus mu k mgx, evaluated from x equals 3.8 to x equals 0. So finally, I can take the square root of both sides to get my v final, which is to say v final equals square root. We have 2 over m, and then we have this, which was our net work integration that we performed, 20x minus 5/2 f squared minus UK mgx. And again, that's evaluated from 3.8 to 0. This is your final answer. The m term right here, that's this 2.6 kilograms right here. The mu k term, we were given that as well. That's the 0.25. And we have the mass term again right here, which we just showed was 2.6 kilograms. G is 9.8. And finally, you just plug in 3.8 for x. And that's how you get the velocity final. So key to this problem, start with a free body diagram. Figure out all the forces that are acting on the object of interest. Treat that object as a point mass where all the forces are acting on that point mass. Have a coordinate system and have an equation for both the horizontal direction and the vertical direction. I used that to get two equations. I sum my forces in y, that gave me the mass times acceleration in y. I sum my forces in x, that gave me mass times acceleration in x. That allowed me to figure out what the normal force was. Figuring out the normal force is key to figuring out what the kinetic friction force is, because the kinetic friction force is both the coefficient of kinetic friction but also the normal force. And then the other real key to this problem is understanding the work energy theorem. And I made a case that the only conservative force in this problem was gravity, but it's acting in the y direction. There's no work in the y direction, because work, you have to think of force acting over distance. And the only displacement in this problem is horizontal, so the only work in this problem is horizontal. And so then I made a case that you have to think of the net force in the horizontal direction, because you have some force to the right by the rope, some force to the left by friction. And so then what I did is I used my original equation that came from the free body diagram to write an expression for the net force in the x direction. And then we were told that the rope tension force that's pulling to the right actually varies as a function of x. And so I substituted that relation into the integral, performed the integration, and because of the work energy theorem, I could say the net work that's done on the block is equal to the change in kinetic energy of the block. And the change in kinetic energy in the block involves what the velocity of the block is both before and after. And so since this problem wants to solve what the velocity is after, and we know that the velocity is 0, i.e. rest, before, then that's going to be our ticket, equating the work to the change in kinetic energy. And so then I showed you the algebra. And just one more time, I just want to be careful here. This term that you see in brackets here, okay, you see how there's this 3.8 and there's this 0. To evaluate that, you have to first plug in 3.8 every time you see x, and then that number you subtract plugging in 0 every time you see x, which simplifies, because in this case, if you plug in 0 every time you see x, it completely vanishes. So you're just going to plug in 3.8 every time you see x, and you're going to multiply it by 2 over m, and then you're going to take the square root of the whole thing. And so that is how you solve problem number 6 from problem set number 6. This is problem number 9 from problem set 6. This is a problem where there is a uniform, and the key word here is uniform beam, which means that the mass is uniformly distributed throughout the beam. And this beam, I'm going to draw an X here. This is bolted. And if you can imagine, there's a mass of the beam itself, and then there's also a mass of a worker that's standing at the end of the beam, and the beam has a length L. And because of the gravity of both the beam and the worker, there's going to be downward forces. And so those downward forces are going to exert a torque about that point you see in X that the beam is bolted to. Before I go any further, though, I want to do a brief review of the concept of torque, because that is a central concept in this problem. And as I mentioned previously, when it comes to, say, circular motion. There's a centripetal force that's required to allow the circular motion to continue. But that's not a force in and of itself. It's just forces that we're already familiar with, but that happen to be oriented in a way that allow the circular motion to take place. And so similarly, ordinary forces we've dealt with, like gravity or like tension, those forces can sometimes cause rotation and sometimes not. And so I want to do a review where I want to turn your attention to this gray circle you see on the left. Imagine that we are looking down, like this is like an overhead view. And what I'm going to do is I'm going to put a point mass, and that point mass I'm going to say is a distance r away, and I'm actually going to call this vector r. It's a position vector. So the magnitude is the length, and that is the radius of that circle, but it also has a direction to it. And I want you to think about, if a force is applied, whether that force would cause a rotation or not. So more specifically, let's say that I had a force that was oriented like so. That would not cause a rotation. It might cause some stretching, but it's not going to cause a rotation. In contrast, if I had a force that was oriented, say, like this, that's absolutely going to cause a rotation. It's going to cause a rotation that is counterclockwise. When it comes to torque, we have the magnitude of the torque, and then we also have the direction. And so we say that if the torque causes counterclockwise rotation, then it's a positive torque. Now, in contrast, if I had a force that was oriented like this, in this case, you can imagine that it would cause a clockwise rotation. And a clockwise rotation is negative torque. Okay, so what I want you to think about now, you saw a situation where if the force is parallel to the position vector, there's no rotation. If it's perpendicular, that's actually maximum rotation. What I want you to think about is, what if, and again, this is a point mass. This point mass is a distance r away from the center of the rotation. So you can imagine that the axis of rotation, if we're looking straight down, the axis of rotation is coming straight out of the screen from your vantage point. So let's say that I have some force that I apply right here. And again, these can be ordinary forces like gravity, like tension. But let's say if I was to just draw a dotted line to kind of show an extension from the position vector, let's say that there's some angle theta. Now, we could take F and we could break F into both its component that is parallel to the position vector. I'm going to call that F parallel. Remember, this is a vector, and so this is the component that's parallel. That, as I showed previously, if the force is parallel or anti-parallel to the position vector, it doesn't cause rotation. If it doesn't cause rotation, there's no torque. It could cause stretching or shrinking, but it's not going to cause rotation. So this F parallel is not going to cause rotation. However, there's also a component of the force, which I'm going to call F perpendicular, and that absolutely causes rotation. So it turns out that the parallel component of the force is going to be F parallel equals F cosine theta, and F perpendicular is equal to F sine theta. When we're dealing with the magnitudes, we can take the magnitude of the force vector in both cases. But do you see this sign right here? This is the key for torque. When we're talking about the magnitude of a torque, So we're not worried about whether it's positive or negative. And again, if it's counterclockwise rotation, it's positive. If it's clockwise rotation, it's negative. But if I have just the magnitude of the torque, then we don't have to worry about the sign positive or negative. We just have to worry about the value. And so the magnitude is going to be whatever the force's magnitude is, but then we have to multiply it by the sine of the angle between the force and the position vector, which is to say that we want the perpendicular component of the force. The component of the force is perpendicular to the position vector. This right here gives us this right here. And then, of course, we also need to take into account what the position vector is. And so I'm going to also put the position vector's magnitude right there. So just to show it in the more common notation, you have the magnitude of the force, the magnitude of the position vector. So in this particular case, this position vector right here, that magnitude is just going to be the radius of that circle. And then you have the sine of the angle between the two, where again that theta is right there. This is known as the cross product. The cross product, if I wanted to say the force crossed with the position vector, then that would equal the magnitude of the force, the magnitude of the position vector, and the sine of the angle between the two. And you don't have to worry about it for this problem, but if you do a cross product of two vectors, the result is a third vector that's perpendicular to the two vectors you crossed. And so the cross product here would have this magnitude, but then it would have a direction that's perpendicular to both the force and the position vector. So as this problem is set up, it would either go out of the page or into the page. You don't have to worry about that though, because we're going to focus on magnitudes. This problem is asking for magnitudes. It's asking what is the magnitude of the torque about the bolt. And again, so imagine the beam is bolted right here, and the problem is asking what is the magnitude of the torque about the bolt. So we're going to have to take into account two things. We're going to have to take into account the mass of the beam itself, and we're also going to have to take into account the mass of the worker that's standing on the end of the beam. The beam has a length L, and we are told that that's 5.20 meters. That's this right here. And we're also told what the mass of the beam is. It's 500 kilograms, and again, it's uniformly distributed. And we also are told what the mass of the worker is. So what's going on now is that we've got a couple of forces that are causing a torque about where the beam is bolted. The more straightforward one, quite simply, is if I represented the worker with some point mass, then there's a gravitational force that is the mass of the worker, G. And so if you can imagine, right, this is some position vector, R, there absolutely is going to be a torque, and that rotation is going to be in a clockwise direction. So there's some clockwise torque that is caused by the weight of the worker being perpendicular to the position vector. So I'm going to start an equation where I'm going to say what is the total torque on the bolt. And again, I want the magnitude. So you don't have to worry about whether it's clockwise or counterclockwise. However, I can tell you right now that for the worker, it's going to cause a clockwise rotation. So there's going to be the torque due to the worker, which is the weight of the worker being perpendicular to the position of the worker relative to where the beam is bolted. Okay, now here's the other thing. We also have the mass of the beam itself. And so the mass of the beam itself can be thought of as, you could break the beam into a bunch of little differential elements, dm. So for instance, the dm that I just drew, it would have a distance away from the bolt that you see in green. If I had a dm, say, right here, so imagine like if the mass of the beam is 500 kilograms total, then every single little dm is a differential mass element that is just simply 500 kilograms divided by however many differential mass elements. And when you're doing calculus, there's an infinite number of these infinitesimally small differential mass elements where you would integrate over the entire object. If you integrate dm over an entire object, you're going to get m for the entire object. But unlike the first dm, I hope you could see that if I was to draw a green line from the bolt to the second dm, it would be right there. That would supply, for the same differential mass element, it's going to supply greater torque, because torque depends on that position vector and how far away the force is acting. For a force that's acting closer to the axis of rotation, it does not give us as much torque, because this R value would be less. If you move further and further away from the axis of rotation, you're going to have more and more torque for the same force being applied. And so similarly, if this number got bigger and bigger and bigger, for the same force, which is to say, if this force remained the same, but this distance where the force is applied gets bigger and bigger, you're going to have more and more torque. So there's more torque from the second differential mass than the first one that I drew. But here's the thing. Let's look at this L over 2. That's the halfway point. So the halfway point of the beam. If I broke that beam, and again, it's a uniform beam, if I broke that beam into lots and lots and lots and lots and lots of little DMs, and I asked myself, what does the torque do to each of these DMs? Well, this one right here, there would be dmg, which is the weight of that little differential mass, and it goes down, has the same acceleration, g, as any object near the surface of the Earth. This little dm right here would also have a dmg. And so they both have the same force acting down, and in both cases, those forces would cause a clockwise rotation. But can you see how the terms are going to be different? One dm is closer to the bolt, and therefore the axis of rotation, than the other. So since this scales linearly, since the torque, but for each of these differential elements, it's just going to be the distance r away from the bolt by a differential mass element by g, then at this halfway point, which I'm denoting right here, as you can imagine, all of the torques to the left are going to be less than all of the torques to the right. But because this scales linearly, what we can do is we can say that because all the torques to the left are a little bit less than all the torques to the right, but it's always a linear change. If this was exponential, if the torque scaled as distance squared from the bolt, then we couldn't do this. But since it's linear, what we can do is we can just treat this beam as a mass at its center, that is a distance L over 2, where we can just have the entire mass of the beam multiplied by G. Because again, you're going to have greater torques to the right, lesser torques to the left. So you can think of this average torque by the beam as just thinking of all the mass at the center of the beam. And if it's the center of the beam, then if the beam is a distance L away from the bolt, then at the center it's L over 2. So I want to simplify things a little bit because we are getting messy here. So I'm getting rid of the differential elements. I'm going to go ahead and color in the beam now as I try to clean things up here. So we've got this beam. It's a uniform beam, so the mass is distributed equally throughout it. That's what allowed me to make the case that like all of the torques to the left of L over 2 are less than all of the torques to the right. So right in the middle is going to be the average torque for all of the little mini masses that add up to be the mass. So that means that I can just treat the beam as a single point mass at its center, where the gravitational force down is the mass of the beam. That's mb multiplied by G. So remember, with the worker, we have the weight of the worker going down, and that's a distance L away from the bolt, and that's going to cause a clockwise rotation. Well, now we have the mass of the beam. As we treat the center of mass of the beam at L over 2, it's also going down and causing a clockwise rotation. So the total torque is not just the torque of the worker, but it's also the torque that comes from the weight of the beam. In both of these cases, do you see how, so this is the position R for the beam, and then this is position R for the worker. In both cases, I hope you can see that the position vector and the force, which in both cases is weight, this is M worker G, it's perpendicular. And so when the forces are perpendicular, that means that theta equals 90 degrees. And the sine of 90 degrees equals 1, which is unity. So when the forces are perpendicular, I can say that the torque due to the weight of the worker standing a distance L away from the bolt, because the beam is of length L, that's just going to be whatever the radius of that worker is, RW I'll call it, and then the mass of the worker and G. Okay, right? This is just the force, which happens to be the force of gravity, right? And then this is the distance from the axis of rotation to where the force is being applied. You don't see a sine theta term anymore because sine of 90 is 1. It goes to unity when they're perpendicular. And now I'm also going to take into account the beam itself. And so remember, we're going to say that the beam can be treated as just a single point mass right at the center of the beam. And then the mass of the beam, gravity, right? So if this was the force of gravity due to the worker, this is the force of gravity due to the beam. And this is just the distance from the bolt, which again is right here, to now L over 2 is where we're going to treat all of the mass of the beam being located for the argument that I presented earlier, because of the beam being uniform in its mass distribution and the torque scaling linearly. So now I can simplify by saying that the radius out to the worker is just L, and the radius to the center of the beam is L over 2. Both terms have a G, so I can factor out a G, and I can say for the worker, the radius out to the worker, right, the distance from the bolt to the worker, that's just L. And then we have the mass of the worker. We're given the mass of the worker, it's 70 kilograms. We're given L, it's 5.2 meters. And then we have the term for the beam itself. The distance to the center of the beam is L over 2. And then we have the mass of the beam. We're given that as well. And I said we were factoring out a G, so there's where the G goes. And so at this point, you just plug in numbers because we've been given everything. We've been given L, that's 5.20 meters. L over 2 is simply that divided by 2, which is going to be 2.6 meters. We're given the mass of the worker, that's 70 kilograms, and we're given the mass of the beam, that's 500 kilograms, and G is 9.8 meters per second. Again, I am talking about magnitudes of torque here. So you don't have to worry about whether it's positive or negative. If you're asked for a magnitude, you just give the amount. You don't have to qualify if it's positive or negative. But when it does come to torque that supplies a counterclockwise rotation is considered to be a positive torque, and torque that supplies a clockwise rotation is considered to be a negative torque. So that is how you solve problem number 9 from problem set number 6. This is problem 10 on problem set 6. There'll be an exam problem exactly like this one. So this problem is a turntable rotating at 100 RPM, which is to say that the angular velocity omega equals 100 RPM, which stands for revolutions per minute. In case you're curious, for a standard record player, the RPM is 33 1/3 revolutions per minute. Probably the second most common is what are called 45s, which are 45 revolutions per minute. So this is going a lot faster than a typical record player would rotate. We're told the mass of the turntable, which I'll call MT, is 1.5 kilograms. We are told the diameter of the turntable is equal to 20 centimeters. And since we see centimeters, let's go ahead and convert now to meters, because meters are SI units. And the way that we do that is that 20 centimeters, if I want to convert to meters, then I need to realize that there are 100 centimeters in 1 meter. Now the centimeters cancel, and so I multiply my columns, so I have 20 by 1 divided by 100. So 20 divided by 100, I have to move the decimal point to the left 2 places. So instead of 20, it would be equal to 0.2 meters. That's the diameter, which is to say that the radius is equal to half of the diameter is equal to 0.1 meters. Now, the omega of the turntable is 100 revolutions per minute. And I'm going to show you that we can actually just leave omega in revolutions per minute. However, just to be thorough, if you want to see how you convert revolutions per minute into radians per second. So if you have a revolution, that's one complete cycle of circular motion per minute. That's what RPM is. And you want to get to radians per second, then one revolution is equal to 2 pi radians. And you see now how revolution cancels. And now I'm in radians per minute, so I'm getting closer. And now what I want to do is I want to convert minutes to seconds. And so 1 minute is equal to 60 seconds. And so the minutes cancel out. So I would take 2 pi and divide it by 60. That's how you would convert. But again, I'm going to make a case that we don't even need to make the conversion for the angular velocity omega. So let's go back and look at this turntable. It's rotating at some angular velocity omega. And what happens in this problem is that, and I'm going to say one block falls right here and one block falls right here. So you can imagine the turntable is rotating at omega. And then let's call that omega turntable. And then these masses fall onto the turntable and they stick. So this is akin to a perfectly inelastic collision, where we saw that if the net forces on a system were 0, then the momentum was conserved before and after the collision. So a little reminder, by Newton's second law, force equals mass times acceleration. And as I've shown in other videos, you can rewrite this as mass times the time rate of change in momentum, dp dt. And so in a perfectly inelastic collision where, say, two particles collide and they stick together, if there's 0 net force, that means that dp dt equals 0, which is to say that momentum is constant. Now, in this class, I've been trying to make a case that once you understand things in a linear fashion, you can quickly adapt to rotation. I talked about how when you had kinematic equations where you had some displacement x, the rotational analog was theta. Some velocity v, the rotational analog was omega. Acceleration a, the analog is alpha. And continuing with that, we had the idea of mass. The analog for that is moment of inertia. And it turns out F, force, the rotational analog for that is torque. And what I'm going to also make a case for here is that momentum P, the analog for that, angular momentum L. So just like I showed you, if the net forces are 0 in a collision, then the time rate of change in momentum is 0, which means the momentum's constant, which means the momentum before the collision equals the momentum after the collision. So I can similarly make a case. I'll change the color here. This is analogous to torque. This is analogous to moment of inertia. This is analogous to alpha. So I can say torque equals moment of inertia, angular acceleration. This right here, mass, again, is moment of inertia, and momentum is angular momentum. So, because we're dealing now with rotation. So torque equals I alpha equals I times the time rate of change of angular momentum, L. And so if the net forces are zero, so think about it. The turntable is rotating at some original angular velocity, omega turntable. All of a sudden, these two blocks fall from above. And by the way, we're told that the mass of each block is 510 grams. And we want to convert that. So there's 1,000 grams in 1 kilogram. So 510 divided by 1,000, we want to make the decimal point go over 3 places. And so that's going to be equal to 0.510 kilograms. And there's 2 of them. And that's what I have marked as these red dots. So they each are on the periphery of the turntable. And so if you can imagine the turntable has a radius r, each of them are a radius, which is, so if you have a diameter d, right, each of those masses are a radius d over 2 away from the center of the turntable. Now they stick. So if they stick, the net forces are zero. There's just action-reaction forces when the masses fall on the turntable and stick. So this is to say that the same way I showed that if you show force as equal to mass times the time rate of change in momentum, and if that equals zero, the momentum is constant, well, I can show you that torque, which I have here in green, is equal to the moment of inertia times the time rate of change of angular momentum. And so if the forces, when those red masses fall and stick to the turntable, if the net force is zero, then this is zero, which is to say dl dt equals zero, because there is a moment of inertia, because there's mass with both the turntable and the masses that fell onto the turntable, which is to say that the angular momentum equals constant. So this means that the angular momentum initial, this is before the masses fall into the turntable, equals the angular momentum after they fall. Which is to say the angular momentum of just the turntable is equal to the angular momentum of the turntable plus the blocks. I've already shown how we have these various different analogs from linear to rotational. So just as P equals mass times velocity, that's linear momentum. Angular momentum is moment of inertia multiplied by angular velocity, omega. So if I know that the angular momentum of the turntable before equals the angular momentum of the turntable plus the blocks, then I know that because angular momentum equals I omega, I can say the moment of inertia of just the turntable, this is before the blocks fall on it, multiplied by the angular velocity of just the turntable is equal to the moment of inertia of the combination of turntable plus blocks, and now a new angular velocity of the turntable plus blocks combo. Because the angular momentum is constant, that's why I can write the equation that I just wrote. So that means that if the moment of inertia changes before and after, you're going to see a change in angular momentum or should I say, you're going to see a change in angular velocity before and after. So for example, if you originally have a turntable by itself that has some moment of inertia it, and then two masses fall on it, that's going to change the moment of inertia. So if the moment of inertia goes up when the masses fall on the turntable, then because of this equality, if this term goes up, to preserve the equality, this term would have had to go down, or vice versa. So let's go ahead and play this out some more. And more specifically, this problem wants us to solve for the turntable's angular velocity in RPM just after the event. And again, the event is when the two masses fall and stick to the turntable. So we want to solve for this right here. To do so, what we can do is divide both sides by the moment of inertia of the turntable block combo, which is to say omega t plus b, that's what we want to solve for, is equal to I turntable omega turn, okay, this is before the masses fell, divided by moment of inertia of the turntable plus block combo, and that is multiplied by the angular velocity omega of just the turntable by itself. So we're going to have a ratio, and I'm going to show you how you can calculate those moment of inertia terms in a moment. But this is a good place to show you that since both the numerator and the denominator here are moments of inertia, then the dimensions cancel out. So this ratio is a dimensionless number. So if I know the original omega turntable before the blocks hit, that's 100 RPM. So that's what this term is right here. So if I leave that in RPM, I'm going to get an answer in RPM because the number in brackets I multiply it by is a ratio where the dimensions cancel out. So even though I showed you how you could convert from revolutions per minute to radians per second, you actually don't have to in this problem. However, we're still not done because we need to be able to calculate what these moments of inertia are. If you encounter problems on the exam, and I already told you there's going to be a problem just like this one, I'm not going to require you to memorize moment of inertias for different objects. You will be given the moment of inertias in a problem. It turns out that the moment of inertia I for a solid disk is equal to 1/2 whatever the total mass of the disk is and whatever the radius of the disk is squared. And we can treat each of these blocks, these red blocks that fell down and stuck, and again, that sticking is like a perfectly inelastic collision where there are forces of the masses sticking to the turntable, but those are action reactions, and so the net forces are zero, and that's what allowed us to treat the angular momentum as conserved, just as we can treat the linear momentum as conserved when net forces are zero in collisions. So each of those masses can be treated as a point mass, and the moment of inertia for a point mass is equal mr squared. So what's left is we need to solve for both this moment of inertia when it's just the turntable and the moment of inertia when it is the turntable plus the block combo. And by the way, I just saw a mistake that I made. I wrote down the angular velocity for the turntable twice. So this is one of the advantages of really waiting until the last minute to put numbers in. It's a lot easier to see mistakes in your symbolic manipulation if you leave things in the symbolic form. Just to review, I hope I didn't confuse you here. I have conservation of angular momentum, which says that the angular momentum of just the turntable equals the angular momentum of the turntable plus block combo. Angular momentum before equals angular momentum after, where the event was that the masses fell down and stuck. And then I said angular momentum can be expressed as I omega, just as linear momentum P can be expressed as mass times velocity. And so that's what allowed me to write down this equation right here, where I can say that the moment of inertia for just the turntable and the angular velocity for just the turntable is going to be equal to the moment of inertia for the now turntable plus block combo, that's the turntable and the blocks on it now, multiplied by the new angular velocity of the turntable block combo. What I did was I divided such that if I divide by this term right here, I can isolate this term right here, which is what I did, because now you see how I've got the angular velocity of the turntable plus block combo. Do you see how this term right here is now downstairs here? And this term right here is, you see the I turntable, that's this term right here. And then the omega turntable term, that's this term right here. I accidentally wrote down the omega turntable term twice. So what you see now here is correct. And now when I say that we have in a moment of inertia, I turntable divided by a moment of inertia, I turntable plus block combo, it's going to be dimensionless because both the numerator and denominator in brackets have the same dimensions. They're both moment of inertia calculations. So it's just a ratio. So if you leave omega turntable in its original RPMs, you're going to get an answer of omega with a turntable block combo also in RPMs. So that's why you don't have to convert. So apologies for that mistake. Going back to the moment of inertias, we have a solid disk. That's what the turntable is. The moment of inertia for that is 1/2 mr squared. And the masses, the little red point masses that fell down, they're blocks as they're stated in the problem, but you can treat them as point masses. They each have a moment of inertia of mr squared. And again, r is going to be the radius from the axis of rotation. Okay, so now what we need to do is we need to solve for the moments of inertias that you see in these brackets right here. And then we'll multiply it by 100 RPM, and then we'll get our final angular velocity for the turntable block combo. So here's how it's done. What we're going to do is we are going to first compute the moment of inertia of the turntable. That's the numerator term right here. And that's easy because it's just a solid disk. And as I just showed you, for a solid disk, the moment of inertia is going to be 1/2 whatever the mass of the turntable is by itself, and then the radius of the turntable squared. The moment of inertia of the turntable plus block combo, once again, it's the turntable, so I can just repeat what I just wrote above. But now I have to take into account those two point masses. Remember, I put them in red following, so I'm going to put them in red here. One point mass would be m block r squared. Each of these is also a distance r from the center of the turntable. So the disk has got some radius r, and because both of the masses fell right on the periphery of the turntable, they're also a distance r away. And there's two of them. So I'm going to add another mb r squared. Do you see how the moment of inertia is different now? I have to account for these two additional masses that stuck to the turntable. Well, that's equal to 1/2 mass of the turntable, radius, and again, we were given the diameter of 0.2 meters, and so the radius is just simply half of that, which is 0.1 meters, plus 2 mass of the block, r squared. So that means that this term right here, that goes right there. And this term right here goes right there. So now you just need to plug in numbers, because for the first that you see in blue circled there, that first moment of inertia for just the turntable, well, you need to know what the mass of the turntable is, but we're given that, 1.5 kilograms. We know what the radius is, it's 0.1 meters. And then for the second one, again, we know the mass of the turntable and we know the radius. The radius is also the same for each of the blocks because they're right at the periphery of the turntable. The only other thing we need to know is the mass of the blocks, and we were given that too. We were originally given in grams, and I showed you how you can convert it to kilograms. So all you need to do is plug in numbers there. And so then, again, since when you take the ratio of a moment of inertia turntable divided by a moment of inertia turntable block combo, since they're both moments of inertia, the dimensions cancel out. It's just a ratio. And if you multiply that by the original angular velocity of the turntable, you will get the new angular velocity of the turntable plus block combo. And I hope you can see, because of conservation of angular momentum, if we have different moments of inertia before and after, then we're going to have different angular velocities before and after. So that is how you solve problem number 10 in problem set number 6.